Anybody with? Everybody's good? Yeah. Okay, so we, I guess, started lecturing last time, but we'll start it up here again. So again, we're going to start with chapter 1. As I mentioned last time, again, we sort of do the atoms first approach here. So we're going to talk all about atoms, electrons, sort of the structure of the atom, and then kind of go through some other things and then go back to things like naming and those type of things. So last time we got into talking about sort of different states and the transitions between, say, solid to liquid to gas. So a reminder, right, we had our solid, which is, again, really in there pretty tight to each other. We then obviously have our liquid state, which is still relatively close to one another and moving around. And obviously, as we talked about last time, we also have our gas state, as everybody is basically broken apart from one another. And as we talked about, a lot of what we deal with is sort of substances going from sort of different phases, and a lot of times sort of the energy associated with it. And as we talked about, not so much energy in this class anymore, but you will in 200B talk about sort of the energy relationships. There are certain processes, again, it is melting, right, as we go from solid to liquid. Going in the opposite direction there, it is freezing. Going from liquid to gas, it's evaporation or vaporization, and obviously condensation there, heading from gas back to liquid. Sublimation, if we skip the liquid part and go from solid to gas directly, and deposition as we go this way from gas back to liquid. I'm sorry, back to solid, skipping the liquid part. As we talked about in terms of energy, and it is putting in energy as you go from solid to liquid to gas, which again, as we talked about, is what is referred to as being endothermic. Opposite is true if we go from our gas to our liquid to our solid, it is exothermic. Energy needs to be released in that case to allow really everybody to kind of come back together. They're not going to have as much energy, and they're going to sort of group together into the liquid phase, and you continue to take out that energy, will go into the solid phase. We talked also about, I think at the end there, that these sort of processes here in the circles, they do occur at the same temperature. So melting and freezing occurs at what is known as the normal sort of melting point or freezing point of a substance, and it does happen at the same temperature. So something like water is 0 degrees Celsius where that happens. Also, evaporation and condensation also occurs at the same temperature. And again, that's the normal boiling point for a substance. And again, for something like water, that is 100 degrees Celsius where that occurs. Any questions on any of that stuff we talked about there last time? What's that? It's an L, actually. So, yeah. So it stands for liquid. Yep. Other questions? Okay. All right, so let's get into this chapter a little bit more. Let's talk a little bit about atoms and molecules. Matter is basically composed of really small sort of particles, and they are what are referred to obviously as atoms. Atoms are really the simplest representation of an element. All our elements there on the periodic table. The smallest sort of unit of any element is an atom. A molecule is a definition basically of two or more atoms that are together. Now, sometimes people, and we'll see this word I think a little bit later in this chapter, get a little confused about the idea of a molecule and maybe a compound. And they can be kind of the same thing, and they can be different as well. And we have really sort of our element in there as well. So elements are really sort of as far back as you could go in terms of substances. You can't break anything down further than elements. Obviously, those are all of our elements on the periodic table. As we'll talk about, obviously, different combinations of elements give us different molecule or different compounds. But the difference between sort of a molecule and a compound is a molecule is just simply two or more atoms that are together. They could be the same atom or they could be different atoms. So what I mean by that is, for example, Oxygen comes as O2. Hydrogen comes as H2. Nitrogen, the way it normally comes by itself without anybody, is N2. For example, fluorine, chlorine, bromine, and iodine. All of these guys comes as twos, which basically means, you know, there are basically two hydrogens that are bonded together. There are two oxygens that are bonded together. They all come as twos. Every one of these guys are what are referred to as being a diatomic molecule. So they're all molecules. Diatomic means two, di means two, atomic means atoms, so two atoms together, there make it up. But because they are all basically atoms of the same element, they're also considered elements. So all those guys there, the O2, the H2, the N2, they are molecules because they meet the basic definition of a molecule, which is two or more atoms together. They're all still elements because they're made up of the exact same element in each case. They are not compounds. Now, a compound is basically the combination of two or more atoms of different elements. So that is a compound. So in a compound, you do have two or more atoms together, but they are of different elements. So for example, if we took something like water, which is H2O, that has basically two hydrogens and one oxygen when you draw it. And this is a compound because, again, it basically contains two or more different elements there together. Is water a molecule? Water is also a molecule because it has two or more atoms. It doesn't matter if they're the same or different elements, so it's also a molecule. Is water an element? Water is not an element here, obviously, because there are different elements involved. So a compound can be a molecule, but a compound cannot be an element because to be a compound, it's got to have different elements involved, so it cannot be an element. Any questions on that there? So much like, you know, sort of the alphabet, if you will, the elements are sort of your basic building blocks of everything. So like in the alphabet, you know, there's only so many letters, but if you put different combinations of those letters together, you do make different compounds. So for example, if we put some hydrogen gas and oxygen gas here together, we will get some water being formed, which again is a compound in this particular case. Any questions on that? These are good ones to remember, that these guys here, by the way, are elements that come again as diatomic molecules. And again, that is how those guys come when they are by themselves. They are not combined with anybody else. That is simply how they come. Everybody else pretty much on the periodic table, as we'll talk about, are what are referred to as being monoatomic. Monoatomic meaning one, so they come as ones, basically, is how they naturally come. Any questions on that? Now, obviously, when we write sort of formulas and stuff like that, we use subscripts to indicate how many atoms of each of those guys. And the subscript, which is the bottom number here, always goes to the guy to the left. So obviously, there's two oxygens here. Something like our H2O would mean that there are two hydrogens. And if there is no number written pretty much in chemistry, that usually means that there is one. So that basically means that there is one of those guys to the left there. Obviously, if we have something like CO2 here, we would have one carbon and two oxygen atoms that make that up. CO2 would be a compound. It would also be a molecule. And once again, CO2 would obviously not be an element in this case. A lot of what we deal with, obviously, in chemistry deals with chemical reactions. Chemical reactions are chemical changes. And ultimately, what that means is what we start with and what we end with are two fundamentally different things. You can't get back what you started with by any type of physical means. That means, you know, boiling, freezing, or anything like that, filtering. And that's what we see here. So if we take a couple of waters here, and we run an electrical current over it, we could actually break these guys back down into their elements of hydrogen and oxygen here. Do a little balancing like it's chemistry here. There you go. So this again is a compound that can be broken down into elements by some type of chemical change that occurs here. So a lot of what we see obviously deals with chemical changes, which are chemical reactions, and we deal a lot with that. Actually pretty, not too hard to do. You could use a 9-volt battery and a little bit of water that has some acid in it, and you could basically separate out the water into the hydrogen and oxygen in this particular case. Obviously, when we reach this point, this is pretty much as far as we could go. We cannot go any further. Obviously, we cannot take those oxygens and hydrogens and break them down. Speaking of reactions, just some general bit about reactions. Obviously, we'll talk more about it when we get to that chapter, but what we start with are what are referred to as reactants. That's the starting material there in a chemical reaction. And what we make on the right-hand side of the arrow are what are referred to as our products, and that is what is formed as a result of a chemical reaction. We also do sometimes use reactions to indicate physical changes that occur. So we're not really making anything new, but we are changing the state. So we will sometimes see, reactions written for physical processes. For example, when we take solid water to liquid water here, we'll sometimes see that. Maybe you'll see a little delta, which means heat. Obviously, heat is basically going from ice to liquid water in that case. It's not really a chemical change. There's no chemical reaction happening. It is still water. Ice is still H2O, right? And water, liquid water, obviously is H2O. They're still fundamentally the same thing, but what we see is a change in the state, like we were talking about there a little bit earlier. So most of the time we use chemical reactions to indicate chemical changes and chemical changes that occur. But sometimes we do use sort of reactions to indicate physical changes that occur. So obviously this would be more of a physical change up here. Any questions on that there? Let's talk a little bit about the scientific method, just briefly. Scientific method is usually a process where we like to, sort of figure out things in chemistry. A lot of times the scientific method really does start with an observation. So perhaps you observe something or something is being observed and you want to sort of come up with an idea as to why that's happening. So you usually will come up with a hypothesis. A hypothesis is usually, well, a good hypothesis is usually a testable sort of a statement as to why something is occurring. Testable meaning obviously you could do some type of experimentation to either validate or invalidate your hypothesis that's happening. And that's usually the next step after you come up with that is some type of experimentation. Once you do an experiment, it will lead you usually back to observations. And those observations, again, may validate perhaps your hypothesis, or it may not. And it may lead to perhaps revision of your hypothesis and maybe further experimentation. So it can be sort of a loop, if you will, at some point. Ultimately, though, hopefully, as you go through sort of that process, you do get to a point where maybe you come up with what is referred to as a theory, or maybe some type of law may come from that. And a theory is sort of a model, and a theory is, so sort of the difference between sort of a theory and a law, if you will. A theory is a model where it can be changed over time. It can be sort of revised over time. Some parts of it may be found to be incorrect over a period of time, and there might be some modification to it as time goes by, and that's where this sort of loop is through experimentation. Maybe not all parts of the theory are correct. We're going to talk here, I think, in this chapter about Dalton's atomic theory. And Dalton's atomic theory is correct in certain parts, but sort of incorrect in other parts of it. Something like Bohr's theory of the hydrogen atom, which we'll also talk about, I think, maybe in the next chapter. That also works really well for hydrogen, but as you move to other elements, it doesn't really work really well and stuff like that. So theories are more things that, generally explain what's going on, but may be revised, may be found through further experimentation to be maybe not correct. A law, on the other hand, is something that, pretty much always happens the same way. It doesn't really get revised or anything like that. So like the law of the conservation of mass, if we start with a certain amount of mass of reactants in a reaction, we will end with a certain amount of products in that reaction. So for example, perhaps obviously you might be familiar with when we have an equation, we balance it, right? And we balance the equation. We have 4 carbons on this side, we should end up with like 4 carbons on the other side of the equation. And those carbons may be in different compounds on the other side of the equation, but since carbon basically weighs 12 grams on the left, it weighs 12 grams on the right, we have that conservation of mass that occurs. Also, same idea with energy conservation, law of conservation of energy. We don't lose or create energy along the way, but we can transfer energy from one place to the next, and that's sort of how we don't lose it or anything like that. So a theory is something that really does sort of explain, sort of an observation, but, like I said, it can be modified. A law is, it's almost like should always happen the same way with everybody, no matter sort of what the situation is. Any questions on that there? And again, law really does summarize what happens in really every situation. Hypothesis, again, a good one should be some type of testable one where you can do some type of experimentation. And again, that theory, it really does explain mostly what is being observed, but maybe is not 100% correct in all situations, and maybe has to be revised. All right, so we're going to then sort of transition here and talk really about the atom. We're going to talk about the atom and We're going to talk about some important experiments that led to sort of our understanding of the modern atom. As we go through, we'll kind of talk about what's important, what you need to know. Greeks really were the first to attempt to explain chemical changes that occurred. They kind of a long time ago thought of sort of atoms. They called them atomos, which is sort of a forerunner to atoms. A lot of early chemistry work was done by Boyle, and we see him in Boyle's law when we talk about gases. He did a lot of sort of quantitative experiments. Quantitative means measurements, yes. Values are taken. Qualitative is really more observations, right? No real numbers or values. So if you're doing a qualitative sort of experiment, which you will do if you take 200B, you do a bunch of what's referred to as qualitative analysis. There's no calculations, there's no measurement. It's simply you look at it and go, oh, it turned purple, or it made a yellow solid, or those type of things. As opposed to a lot of what we do in this class, and a lot of chemistry labs, this was quantitative. We measure out a certain mass of something. We get volume readings and those type of things, which are quantitative, which are measurements. So there are 3 sort of important laws, that are the fundamental of, sort of the idea of the atom. And we kind of touched upon here just a second ago on some of these. The first one is the law of conservation of mass. And as I mentioned, mass is neither created nor destroyed. And that's really why we do sort of the whole balancing of equations. We should never lose an element along the way. So we do have that conservation of mass. And that's really for chemical reactions. The only sort of reactions, that occur that we do not really have that in a sense is nuclear reactions. And nuclear reactions you don't have the conservation of the elements. They actually do change from one element to the next as they're decaying through the process. So we don't really necessarily have that conservation of elements, but definitely in all chemical reactions, like I said, if you started with like 6 oxygens on the left, you should definitely have 6 oxygens on the right, again, in different things and stuff like that. The law of definite proportion is the idea that a given compound always contains exactly the same proportion of elements by mass. So something like water always has basically 2 hydrogens for every 1 oxygen. And the mass of hydrogen is about 1. So you got about 2 grams of hydrogen for every 16 grams of oxygen, which means in terms of proportion, for every 1 gram of hydrogen, you have about 8 grams of oxygen that are there. No matter where you get your water from, no matter what it's bottled in, it's always going to have that same ratio when we're talking about something like water as well. The same thing, obviously, if you had something like CO2, again, there's basically one carbon atom for every 2 oxygen atoms. And again, that's basically 12 grams of carbon for every 32 grams there of oxygen that is present in that particular case. The law of multiple proportions is when 2 elements form a series of compounds, the ratio of masses of the second element can always combine with 1 gram of, 1 gram of the first element to give you basically whole numbers. The idea there is when we write formulas and stuff, we always end up with a ratio of whole numbers of these guys. We never end up with like 1.5 carbons to like 2 oxygens or anything like that. So elements are always able to combine in whole number ratios. Ionic compounds, which are metals and nonmetals, are always able to do that in the simplest way to achieve that. That is why, we get something like sodium chloride. If you put 2 sodiums and 2 chlorides together, that is really the same if you reduce that down to 1 sodium and 1 chlorine to make something like sodium chloride. And that is definitely always how ionic compounds, which are metals and nonmetals, always come together. Things that have charges, positive, negative charges, when they come together, they always come together to balance out the charges in the simplest whole number way that they could achieve that. And for covalently compounds, they always also come together in whole number ratios. So you'll never get sort of a half of an element or an atom of an element happening. Any questions on that? So then let's talk about some of these early experiments. Really a lot of early work there was done by a guy named Dalton. I should say Dalton there. Got a little high, I think. John Dalton. And he had unusual talent for math at an early age. He kept records of the weather every day of his life. He woke up, wrote down the weather. Seems like a nice guy. He never married, surprisingly, but he did like to go bowling on Thursdays, which is a super important thing. Definitely will show up on an exam. It is not Friday. It is not Cosmic Saturdays. It is Thursdays. He went to go bowling on that. But really what he is known for, now you don't know if I'm kidding or not, and I'm really not kidding, by the way. What he's known for is basically has a precise definition of sort of what we call atoms. So really what he's known for is sort of Dalton's atomic theory, and we're going to go through sort of these parts of it here. And you do need to know sort of the different parts of Dalton's atomic theory here. He said that each element is made up of tiny particles that are called atoms, which is still correct, obviously, today. Atoms, as we'll talk about here in just a second, obviously have an internal structure, but they are the basic units of pretty much of all elements. He said atoms of a given element are identical. The atoms of different elements are different in some fundamental way. So this is one thing that is not necessarily correct. So this is why, again, it's Dalton's atomic theory. It has been sort of revised over the years. The part that's not really correct still today is sort of the idea that all atoms of a given element are identical. There is something there we will talk about as well that are known as isotopes. So the appearance of isotopes sort of made that part of Dalton's atomic theory not correct. Isotopes are pretty much the same element, but they have different masses. So clearly they're not identical if they have different masses, but they are still the same element. As we'll talk about, what makes them have different masses is they have different numbers of neutrons. So that also tells you that they are not perfectly identical to each other. So sort of the discovery and the existence of isotopes made sort of this part of Dalton's atomic theory not correct, the part where every one of the same element are identical. But obviously, atoms of different elements are different from each other. That is obviously okay. Chemical compounds are formed when atoms of different elements combine with each other. A given compound always has the same relative numbers and types of atoms, and that is correct as well. Again, you know, that is basically how we form compounds. It's basically a combination of different elements. We could even have, you know, the same elements involved, but the way they are bound together or the different numbers of those elements do give you different properties. You know, you could have something like NO2 or, you know, N2O. These are obviously the same two elements involved, but these are two different compounds that are there based on the idea the first guy's got two oxygens, only one nitrogen. The other guy's got two nitrogens and one oxygen. Even though they are composed of the same elements, they do present different compounds which have different sort of properties associated with them as well. Chemical reactions involve the reorganization of atoms, changed in the way they are bound together. That is correct. So again, when we do have a chemical reaction, the idea here is, you know, whatever we start with in terms of elements in here, we do end up with sort of the same elements, but they are in new compounds, probably on this side in most cases. So they basically just rearrange, like we said, we don't lose anybody along the way, and we just form new things with different combinations of those guys. As obviously we see here when we take something like, and by the way, this could also be compounds as well over here. H2 or O2 gives us H2O. And once again, if we do the balancing, we had 4 hydrogens we started with, 4 hydrogens we ended with, 2 oxygens we started with, and those guys give us 2 oxygens that we end with as well. So we get all the same elements that we started with, but again, sort of rearranged. They obviously have very, very different properties. Hydrogen gas and oxygen gas has very, very different properties than water, obviously, right? A little explosive on the other side, not so explosive on that side. Same thing, by the way, when we, you know, you talk about sort of the idea between elements and, you know, the compounds that they make. This is sodium metal, which is like a soft, shiny-ish type metal. This is chlorine gas, it's a G, which is a toxic green gas, right? And by the miracle of chemistry, they come together and make sodium chloride, which is like a salt, right? So it's, you know, not too bad. Put it on your fries and everything's okay. You definitely would not want to put just the sodium metal on your fries, right? Or the chlorine gas on your fries. Probably wouldn't be so good for you. But again, very, very different properties. And that's usually what happens with compounds. They have very, very different properties and the elements from which they come from. As they come together, obviously changes those properties. Any questions on that there? The atoms themselves, again, are not changed in a chemical reaction, as we just talked about, sort of that conservation of those elements. All right, so let's talk a little bit about some things here. Which of the following statements regarding Dalton's atomic theory are still believed to be true? Elements are made up of tiny particles called atoms. That's good, right? That is basically what is made up of. All atoms of a given element are identical. That is not true, as we were just talking about, right? That is, again, the existence of isotopes and the different masses. A given compound always has the same relative numbers and types of atoms. That is still good. Again, atoms are indestructible. That is also not correct. Again, as I was talking about a little bit earlier, something like a nuclear reaction. We can really change an atom from one element to the next. Why that happens, by the way, and again, you'll have a whole chapter on nuclear chemistry in 200B if you take it, but why that happens is basically in a nuclear reaction, we are changing the protons and neutrons, the guys inside the nucleus, and that gives us different elements. In a chemical reaction, which is what we deal with pretty much in this class, all chemical reactions, what we deal with are actually electrons, and electrons really don't have any effect on the atom changing elements or the guy changing from one element to the next. So what we deal with, and mostly in chemistry, are chemical reactions that deal with bonds and electrons. The core of what makes something an element is actually what's in the nucleus, which is our protons and stuff like that. So it's only in something like a nuclear reaction that we actually see some changes to those and stuff like that. Any questions on that there? So I guess to answer this question, 1 and 3 would still be correct today. And again, what we talked about, this is a theory. So as time went on, obviously it was sort of revisited. Any questions on that there? Okay. So some other laws, or theories that we come across are really sort of laws that happen. We'll see some of these guys for sure when we get into gas laws. Guy-Lussac's law measured that under the same sort of pressure and temperature situation, the volume of the gases that reacted with each other were related to the number of moles of each of those guys. And Avogadro basically said that you have the relationship between volume and the number of gases that you occur together are equal to each other. So if we take, say, 2 volumes of hydrogen and combine it with 1 volume, we will get sort of 2 volumes of water that occurs. This is sort of the same idea as what we just looked at. We have 2 hydrogens plus oxygen gas gives us 2 waters. So we could have 2 molecules of hydrogen gas reacting with 2 molecules of oxygen forms 2 molecules of water. We can also do what is referred to, as we'll talk about later on as well, sort of a mole to mole relationship. 2 moles of hydrogen gives us 2 moles of oxygen, gives us 2 moles of molecules. So this sort of representation, as we'll talk about when we get into sort of the gas chapter, as basically the molecules increase, so does the volume of those guys in those situations as they're sort of flying around, as all these guys are gases in this case. So the volume and sort of molecules are related to each other through Guy-Lussac's law. All right, we'll get into that a little bit more next time, or next when we get to the gas chapter. Here is the picture of sort of Dalton's atomic theory and sort of what he envisioned, again, in terms of compounds. And in each of these cases, really the 2 elements involved are nitrogen and oxygen. And again, very different sort of properties occur depending on the different ones that you have. So if you had just NO versus NO2 versus N2O, again, even though these 3 are composed really of the same 2 elements, the combination of them do give sort of different properties and give us different compounds. It's kind of like the idea again with the alphabet, 26 letters, and obviously, you could use the same letters to make different words and stuff like that along the way that have different meanings, obviously. Now, based on Dalton's atomic theory, several things were sort of believed about the atom. The atom obviously is that basic unit of the element that could come into chemical combination. A lot of investigations along the way since that time has revealed that obviously atoms contain an internal sort of structure, and that internal structure basically means that they have some what are referred to as subatomic particles. So even though atoms are, by the way, extremely small, they have even smaller sort of particles that make them up. And three sort of particles came to light that we might be familiar with. We have electrons, which are negatively charged. We have protons, which are positively charged. And we have neutrons, which basically have no charge. These three guys pretty much make up atoms of all elements except for hydrogen. As we'll talk about, hydrogen actually only has protons and electrons, no neutrons. But everybody else has basically all three of these particles that make them up. We're going to now talk about certain experiments that led to sort of the understanding of these particles and sort of where they are in the atom. And really the first sort of particle that we are going to talk about is really the electron. And the electron, which is negatively charged. A lot of really sort of good discovery about electrons came about with the use of what are referred to as cathode ray tubes. They're sometimes referred to as CRT tubes. CRT tubes is basically a tube that has sort of an electrical field, positive and negative sort of side to it. And one really important thing in chemistry that we see a lot and a lot of interactions that occur in chemistry is a very basic interaction, which is sometimes referred to as electrostatic interaction. Electrostatic basically means, for example, opposites attract. So much like in life, if you get two sort of positive people together, that's kind of annoying. They don't want to be around each other. They repel each other. You get two negative people, they really don't want to be around each other as well. But when you get a positive and negative person together, they are attracted to each other, right? The whole opposites attract thing. So in chemistry, if you have something that is positive, it is attracted to something that is negative. And obviously, like I just mentioned, they will repel each other. If you have something that is negative near negative, they definitely don't want to be near each other. If you have something that is positive near positive, they also do not want to be near each other. A lot of interactions that we talk about is this sort of interaction, the positive negative attraction. It is actually, as we'll talk about, what holds together an ionic compound, what holds together a metal and a non-metal is actually just that attraction between the positive negative charges. There's absolutely like no sharing of electrons or anything like that. It is an extremely strong attractive force that occurs. So when we have a cathode ray tube, it shoots a beam of negatively charged electrons, which basically would be heading towards the positive side of the cathode ray tube. A lot of times they'll put some type of fluorescent material on there so you can actually kind of see it as it hits. You may be familiar with CRT tubes. You might be old enough, or maybe not. I don't know. Older TVs, by older I mean not like plasmas, but older like, you know, TVs that have like the big backs to them and stuff like that. Those are CRT TVs. Old computer monitors that also kind of like come out in the back and stuff like that. Those are CRT tubes that are in there. Obviously, like our TVs now are not CRT tubes, but the older sort of TVs and computer monitors were CRT tubes. And a lot of work was done by a guy named Thompson. He did a lot of work using the CRT tube. And what he was able to determine by using the CRT tube was the charge to mass ratio of an electron. So the very first sort of understanding of an electron, or really kind of big part of understanding of electron, came from Thompson, who did work with the CRT tube and was able to figure out the charge to mass of a ratio of an electron. That is definitely something that you need to know, yes. Here's a much prettier drawing, I suppose, of a CRT tube. And again, this field it can be affected obviously by electrical field because they are charged particles, right? Something like an electrical field can also have an effect on particles if they do have charges. So if I shoot a particle that is positively charged, it would kind of bend towards the negative side, right, of the electrical field because it would be attracted to it. If I shot like a particle through an electrical field that was negatively charged, it would bend towards the positive side because it should be attracted to it. Then obviously if I shot a particle that just went straight through that's undeflected, that would have really no charge associated with it. So the use of electrical fields and even magnetic fields, which sort of operates similar to that, is used a lot in these earlier experiments to sort of manipulate certain particles based on their charges to help them do certain things. Now, Thomson there figured out the charge to mass of an electron, and it came to minus 1.76 times 10 to the 8. C is a coulomb, it's a unit of electrical charge, and G is grams, which is obviously a unit of mass, and that is the charge to mass of it. There he is staring at his CRT tube right there. And that's why the parents years ago used to say, don't sit in front of the TV because it is shooting things at you. And they were not actually too wrong on that because they had CRT tubes sort of in it. Now, this was a good step in terms of understanding some parts of the electron. The next sort of major experiment that sort of helped us understand a little bit more about the electron was done by a guy named Milligan. Milligan did what is referred to as the oil drop experiment. And it is pretty much what it sounds like. So he took a container where it had basically an electrical field. And he basically shot droplets of oil in here. He sort of atomized them, heated them up really good. And there was like a little hole here where the oil droplets would come through. And just by natural, the oil droplet you would expect obviously just to fall down, right, by force of gravity. What he was able to do in this sort of experiment was he was able to really adjust the electrical field within that sort of container to a point where this oil droplet pretty much just kind of hung there. It didn't go up, it didn't go down. He was able to really sort of dial it in because as the oil droplet comes through the container, it kind of starts to drop by gravity there, picks up some charge, and he was able to sort of dial in the electrical field in that container to sort of keep the oil droplet from falling. What he was able to do based on that was he was able to determine the charge on electrons. So Milligan, doing this oil drop experiment, was able to determine what the charge of an electron was. And that was really important if you take it in combination with Thomson's experiment, who did the charge to mass. And now we have Milligan, who basically figured out the charge of an electron. Using the results of both of those experiments, you can take the charge of an electron and divide it by the charge to mass of an electron. The charge will cancel. And what those experiments leads us to understanding in terms of the electron is the actual mass of an electron. So taking both of those guys together, the mass of an electron could be calculated. Any questions on that there? In case you missed it, let me zoom in. There we go. So here's again the charge of the electron. Again, a much prettier picture of his container than what I drew. But again, the oil comes in here, starts to drop by sort of gravity, adjusting that electrical field, keeping that sort of oil droplet there, able to really figure out the charge of an electron here, which again is there. And taking those guys together, like I said, you're able to really calculate the mass of an electron. And we find that the mass of an electron here is 9.09 times 10 to the minus 28 grams. And that is obviously the mass of an electron. And obviously an electron is negatively charged. Is that a really large number or a small number? is a really small number, right? It is like 28 places that way, right? So like 27 zeros in front of that. So it's a very, very small number. So far, we now understand our electron has a very small mass. It's also negatively charged. And again, from those two really important experiments, Thomson and his CRT tubes got our mass, charge to mass. Our Milligan that got our charge doing the oil drop experiment, we're able to figure out the mass of an electron. Any questions on any of that? So those are the three things you should definitely know. The Thomson experiment, the Milligan experiment, what came out of both of those, and obviously you don't need to know the actual number in terms of the mass of an electron, but that was sort of the result of putting those experiments together. Any questions on that there? Okay. So now that we understand a little bit about the electron and that is negatively charged, we're now going to focus on sort of the experiments that led us to the understanding of sort of the proton and the nucleus of an atom. It was definitely believed through a lot of these experiments that we've just talked about and some others that the atom definitely contained electrons and that the atom was electrically neutral, which means if we already know at this point electrons are negatively charged and it is electrically neutral, the atom must contain something that is positively charged, right? To sort of balance out the negative charge of those electrons. So sort of an accepted theory of our model of the atom about this time was one that was actually proposed by Thomson. And it is what is referred to as the plum pudding model of the atom. And basically the early idea of the atom was we definitely know that there are electrons. So we got this sphere and we know that there must be sort of positive aspect of the atom to balance out those negatively charged electrons. So the idea was that the atom was a sphere of positive charge where we have all this positive charge really just sort of spread out over the atom. And sort of within that positive charge, what we have embedded inside are these negatively charged electrons. So we got these negatively charged electrons embedded inside the atom. And it was believed at this point in time that most of the mass of the atom was actually the electrons, actually made up most of the mass of the atom. And this is what is commonly referred to as the plum pudding model. Plum pudding is a dessert of pudding and raisins inside. And, you know, the guy looked at it and said, that's probably what the atom is like, this kind of squishy positive charge that's really spread out and diffused over the entire sphere with these sort of like the raisins, these electrons embedded inside. And again, here's the prettier picture of that. This is the early model of the atom, and it's really sort of the accepted model of the atom till sort of the next major sort of experiment that came along that helped us maybe understand a little bit better, you know, what is going on here. And that next sort of biggest experiment, or important experiment, was one that was done by a guy named Rutherford. Rutherford did what is referred to as a gold foil experiment. And the gold foil experiment is the idea where he took pieces of gold foil and he basically shot what are referred to as alpha particles at it. So there basically is sort of three types of radioactive particles that was used a lot in sort of early experiments. And there are alpha particles, which are positively charged particles. They're basically helium. There are beta particles, which are negatively charged particles, which are like electrons. So that's alpha. That's beta. And then there are gamma, which rays, which have no charge. And so these are three really sort of important radioactive sort of particles. There's used a lot in these sort of experiments. And obviously, as we just talked about a second ago, you know, when we have something like these guys and we put it through an electrical field, something like the alpha particles should be attracted to the negative side. Something like the beta particle there should be attracted to the positive side. And something like the gamma would just, again, kind of sail through with no deflection or anything like that. So he basically shot these alpha particles from a radioactive source at pieces of gold, foil, and other metals. And his idea was obviously looking at the atom from the Thomson model of the atom that we just saw there, which was the plum pudding model. And what he expected to happen was, because he's going to be shooting these alpha particles at this guy, that positive charge is really sort of spread out in this idea of the model all over the atom. So it's kind of like if I took this piece of paper here and it wasn't all ratted, and I held like both ends, or somebody held both ends really tight, right? And we shot like a pen at it really hard, right? And really fast, it would find its way through there, right? But there would be some deflection as it sort of went through, right? It would probably be able to pop through that. And that's sort of what they expected to happen when they did this. They expected to shoot these positively charged alpha particles and really see it go through, because they're kind of heavy, they're moving pretty fast. And they sort of expected it to kind of go through the atom with some resistance, obviously, because again, we're shooting sort of positive at positive. But again, because the positive charge is spread out, you know, it's going to be able to go through with some resistance that occurred. And when they did this experiment, they were actually really surprised by what they saw. And what they did see was that, for the most part, the alpha particles, which is coming out of the source here, coming through here, went through the piece of metal pretty much undeflected. And that's what we kind of see on this little this guard here, that most of the atoms just kind of went through no problem. They just kind of sailed right through. They also saw something that was also really surprising to them. In addition to that, that most of them went through undeflected. They saw that every so often they would have an alpha particle kind of bounce off at a pretty large angle, which is why we see some of these guys hitting out over here at these large angles from going straight through. And every so often they would even, for example, head on back, you know, from where they came from as well. So this is really surprising to them based on sort of the idea of Thomson's model of the atom. They definitely expected them all to go through. So if we think about it, the ones that went through pretty much undeflected, what did they hit? They pretty much hit nothing, right? If you throw something, there's nothing in the way, it's just going to go straight, right? So the idea here is obviously all these guys that basically sail through with no problem hit pretty much nothing, right? Are empty space, right? Now, in order to make this alpha particles, for example, bounce off at these really, really large angles, or even come back to a source, since these alpha particles are really, really positive, it would have to hit something that is very positive, negative, something with no charge. What it has to hit to make it bounce off like that? It definitely has to hit actually something that is very positively charged, because the alpha particles are positive. It would have to hit something of the same charge to be repelled at those really large angles. Obviously, if it was something that was negatively charged, it would actually just stop, right? It would be attracted to it like a magnet. So in this particular case, to explain, you know, these guys that bounce off at these large angles, it had to hit something that was definitely very positive. So the idea, you know, of like this paper, like when we hold it and it kind of shoots through, and if this was all of our positive charge, you know, in the atom, as we just talked about, you know, it would go through. But if we took, you know, this paper and we folded it, for example, all of our positive charge, instead of all over the entire atom there, right? Where they say you can fold a piece of paper 6 times, 7 times before you can't do it anymore. All right. So if I took all my positive charge from being the entire paper to just this small part, right? And I threw something at it like a pen, it's now going to bounce off, right? Because it's very, very densely positive, and it's definitely going to act as a reflection to that positive guy coming through. So these results here that Rutherford saw was really surprising. That again, most of them went through with very little to no deflection. Again, they did see, as we talked about there, that every so often we would get these sort of large angle deflection that would occur. And it compared it to sort of shooting a gun at a piece of paper and having the bullet sort of come back. You know, you wouldn't expect that based on Thomson's model. So basically what this meant was they had to really kind of move away from the idea of Thomson's model. And this experiment really sort of proved that Thomson's model is not really correct in its aspect. And they had to come up with really a new version of the atom. And that new version of the atom is a couple of things that we've just talked about. And it's really sort of the modern version of the atom. He explained his observations from his experiments as basically most of the atom is empty space. And again, that accounted for why those particles, alpha particles, went through with no deflection. He also accounted for why we had those guys bounce off at the really large angles, that there was definitely a core part of the atom that was very, very densely positive. And that really is, as we learned a little bit later, that is where our protons are hanging out in our nucleus. And those guys are positively charged. And later on in like the 30s, 1930s, that is where we found that neutrons are also in there, which has no charge. Electrons are outside of the nucleus at some point, and the electrons are really traveling in that empty space. So that is where we have our electrons traveling around the nucleus in that empty space. And another very major difference between Thomson's model and sort of our correct model here of the atom is, unlike Thomson's model where he said electrons made up most of the mass of the atom, it is actually the nucleus that makes up most of the mass of the atom. So most of the mass of the atom is the nucleus. Within the nucleus is where we have our protons and our neutrons, and they're responsible for most of the mass of the atom. So our sort of structure of the atom looks like this. We have our nucleus, has protons, and later found to have neutrons. Obviously, neutrons were not found at this point. They were believed to be in existence, but not really found until 1930s. Electrons are traveling. By the way, when we have electrons and a nucleus here, electrons do not travel in pretty circles. Electrons travel randomly about the nucleus. We'll talk about it in another chapter as well. They do not travel in circles or anything like that. We'll talk about it in another chapter, but really at any given time, you don't know exactly where a particle like an electron is or how it's moving. And it's what's known as Heisenberg's uncertainty principle. The more you know about its location of something like an electron, the less you know about how it's moving in terms of its velocity and vice versa. You know, they kind of go opposites of each other. So you definitely need to know about Rutherford and his gold foil experiment. Rutherford shot what at the atom? He shot alpha particles, yes, not a pen. Usually I deal with expo pens that people write on the test. Hey, they shot like expo pens at the atom and stuff like that. I don't think they had them back then and stuff like that. So he shot those alpha particles. So you do need to know, obviously, Thomson's model of the atom, the plum pudding, what it was sort of developed. You need to know the idea of what Rutherford did with the gold foil experiment, what he thought was going to happen, what actually did happen, and clearly you need to know, obviously, the really modern version here of the atom and the structure where everybody sort of is. Any questions on that there? This is just a table sort of summarizing some of the stuff, obviously, we just talked about from the different experiments there. So let's talk a little bit more about the protons, which obviously are in the nucleus of the atom. And it was found that through experiments in the nucleus, we had those protons which are positively charged, which accounted for the positive charge that we do see in the nucleus. And it had a mass of 1.67252 times 10 to the minus 24. And if you remember, our electron was something like 909 times 10 to the minus 28 grams, right? And this is about 1,840 times heavier than an electron. By the way, when you look at a negative exponent, the smaller negative exponent is a larger number. The guy on top there is only 24 places to the left with zeros. The guy on the bottom there is 28 places to the left with zeros. So the negative part of that exponent is important. And that also accounts for why in Rutherford's model and sort of the current model that most of the mass of the atom is made up of what's in the nucleus, since every proton is 1,800 times or so heavier than any electron flying around. It makes sense that it's in the nucleus, and that is the most of the mass of the atom. Now, it was believed at this point in time that the atom is very small to begin with, but the nucleus is even smaller than that. You can think of sort of the atom as the size of a big football stadium. If you ever been to the Superdome, it's a very big football stadium, very high seats, very angled seats. You feel like you're going to fall off when you sit in those seats. And like the nucleus is like a little marble there on the 50-yard line in the middle of the field and stuff like that. So a lot of empty space, very small, but very densely positively charged nucleus in the center of it. Now, it was also believed that in addition to protons, that there was another particle that was in existence in the nucleus. And it wasn't until 1932 that a guy by the name of Chadwick, who did a lot of experiments with radioactive sort of particles, like that came off like X-rays, and also sort of had gamma ray sort of properties as well. And he discovered basically the neutrons, and the neutrons have a mass of 1.6749 times 10 to the minus 24. The reason both of those numbers go out really, really far in terms of decimals is it shows that the neutron actually is the heaviest of all three particles. It beats the proton just barely, as we just saw there. The proton was 1.67252. So they're very close in mass, but the neutron is slightly heavier than the proton. So that is also something you need to know. As I mentioned before, you don't need to know necessarily the actual numbers. They might even be provided for you, but you do need to know that it is actually the neutron that is the heaviest, followed very closely by the proton, and the lightest of the subatomic particles are the electrons. It's the lightest. So obviously you need to know about these three subatomic particles, some of the experiments that help lead to their understanding of where they're located, and obviously the charges and which one is the heaviest and the lightest. Any questions on that there? And there's a table of each of those guys. All right, so just to summarize, where we find all these guys in our modern sort of atom, once again, electrons are found outside of the nucleus and are negatively charged. Our protons, which are positively charged, found inside the nucleus, along with our neutrons, which have no charge and are found inside the nucleus as well. Is there an attraction between the nucleus and our electrons that are flying around on the outside? Is there attraction between those two things? There is. The electrons are negatively charged, right? The nucleus is overall positively charged. So there is an attraction, as we'll talk about in later chapters. That's why certain electrons are involved, for example, in bonding, and other electrons are not involved in bonding, depending on really their location and relative distance to the nucleus. Ones that are very, very close to the nucleus, as we'll talk about, are sometimes referred to as core electrons, and those guys are right on top of the nucleus or near the nucleus, which means they're going to be really attracted to it and going to be held really, really tightly. There are other electrons that we'll talk about, which are referred to as valence electrons, which are higher in energy, a little further away from the nucleus. So obviously a little further away, not going to be held as tightly, and those guys are free to sort of participate in bonding, either ionic bonding or covalent bonding that we'll talk about. Again, it's kind of like a magnet, right? If you take a magnet really close to something, right, it's going to gobble it up, right? But if you have that magnet kind of far away, it's not going to really kind of grab it, depending on how strong your magnet is. So it's sort of the same idea with electrons. The kind of the further they get away from the nucleus or are away from the nucleus, they're not going to be held as tightly, and then obviously any electrons that are near the nucleus will be held a lot tighter than those guys that are further away. As I mentioned, the nucleus is small compared to the overall size of the atom, but very, very densely positive, and accounts for almost all the mass there of the atom. And here's sort of our idea picture of the atom. Here's our nucleus, obviously where our protons and electrons are. This sort of redness, if you will, is what is sometimes referred to as that empty space, or the electron cloud, if you will. And that's where our electrons are randomly sort of moving about in that area. When you see a picture like this, I guess it does come up a little bit up there. It's kind of the darker areas, or areas where there's a higher probability of sort of finding an electron. Not really sure exactly where it's at or how it got there, but there's a higher probability of finding it. And as you can see, it's much darker. And as you sort of fan out, there's sort of a lesser probability of finding electrons in those areas of the atom. And sometimes referred to as an electron density map, something like this, where you kind of see the different shadings of that color. Darker color meaning a much higher probability of finding it. Any questions on the atom or what you need to know? So just to review, you need to know obviously Dalton's atomic theory, the different parts of it, what's still correct, what's not correct. You need to know the sort of experiments from like Thomson, Milligan, and what came out of those in terms of the electron. You need to know Thomson and his early model of the atom, which is the plum pudding model, what it was. And obviously you need to know Rutherford and his experiments and what came out of it, and obviously the modern and correct sort of version of the atom as well. Any questions on any of that stuff you need to know from here? Okay, so let's talk a little bit more about some parts of the atom here. As I mentioned before, you know, for the most part in chemical reactions, which is what we deal with here, it's really all about the electrons. So a lot of the atom and the chemistry and the reactions that they undergo are really those electrons. No chemical reaction involves the protons or neutrons. It's just those electrons that are involved. And that's why pretty much all chemical reactions are simply whatever we start with, we're just going to break all the bonds, which are all electrons based, and we're just going to reassemble on the other side, which is also making bonds, which is all electron based. So everything in sort of chemical reactions are electron based. So that brings us to some important numbers in terms of the atom. And the first thing we're going to talk about is one of the ideas there of isotopes. And as we touched upon earlier, when we were talking about Dalton, isotopes are really the same element, but they have different masses. And they are atoms with the same number of protons, but different number of neutrons. So they have different numbers of neutrons, which gives them different masses and makes them be isotopes of each other. They are identical a lot of times in chemical properties, and that's because, again, in most cases, chemical reactions involve the electrons, not our protons or neutrons. All atoms have protons, electrons, and neutrons, as I mentioned, except for hydrogen, and you can have different isotopes of the same element that have different numbers of neutrons. So this is a sodium atom. It has 11 protons and 12 neutrons in the case over here. The guy on the right here, which is sodium 24, so that's sodium 24. And this is what is referred to as sodium 23, has 11 protons and 13 neutrons. So because guy on the right has a different number of neutrons, they are isotopes of each other. If you had to take an educated guess based on these two numbers, is it the protons or the neutrons that's most important in terms of what element we're talking about? It is the protons, right? The guy with 11 on the left is sodium. Guy with 11 on the right is sodium. It is the number of protons that determine what element it is. So that's why they're both the same element, because they really have 11 protons. Neutrons, electrons do not determine what element you're dealing with. It is always the protons that are the ones that determine the element that you're dealing with. So speaking of that, that is what is also known as the atomic number. And the atomic number is sometimes abbreviated with a Z. The atomic number's definition is the number of protons that you have in the nucleus of an atom. The atomic number can be found on the periodic table. So if you go to the periodic table and you look at something like our friend hydrogen, right there's number 1, That would be the atomic number for hydrogen. If you go to the periodic table there and look at something like oxygen, that is number 8. That would be its atomic number. As you can see there, if you look at something like nitrogen, which is right next door, there would be number 7. It has 7 protons. If you look at a periodic table and you look at all the atomic numbers that are listed on the periodic table, there's absolutely none that repeat. And that is why protons are the most important in terms of determining the element. You will never ever have an atom of nitrogen with 8 protons, because the person with 8 protons is actually oxygen. Yeah, so nitrogen can only have 7 protons. And that is why when you get into something like a nuclear reaction, you change the number of protons. It now is no longer nitrogen. It becomes perhaps something else. But in chemical reactions, because all we're dealing with is electrons, those 7 protons for, say, nitrogen are safe. Nothing's going to change. It's just the electrons. They're going to perhaps change along the way. Now, because when you have a neutral atom, if it is neutral, the same number of positive and negatives need to equal each other, which means when we think about an atom, there basically is protons which are positively charged, or electrons which are negatively charged, and obviously neutrons have no charge. Which means if I know the atomic number for a neutral atom is 7, it would definitely have to have an equal number of negatively charged electrons to make it equal 0. So a neutral atom of nitrogen would have 7 protons and 7 electrons, which obviously equals 0, right? When you take the positives and negatives together as well. The actual definition, though, is if you ask somebody, what is the definition of the atomic number? It is only the number of protons. Second to that is if you're talking about something that is neutral, it will also tell you the number of electrons. So sometimes people think the atomic number is protons and electrons, the number of those guys, and it's not. The actual definition is just protons. But if you're dealing with something that's neutral, it will also obviously tell you how many electrons that it has. Any questions on that there? Now, the mass number is another important number. The mass number is the number of protons and neutrons that an atom has. So the mass number, which is sometimes abbreviated with an A, is the number of protons plus the number of neutrons. And if we take that together with our atomic number, which is the number of protons, and we simply subtract those two numbers, protons cancel, and that is how we can figure out the number of neutrons that are there. So if you take the mass number and you subtract it from the atomic number, that will tell you the number of neutrons that you have in a particular atom. When you calculate all those things, the mass number, the atomic number, the number of protons, number of electrons, number of neutrons, they all should be positive whole numbers. So they all should be positive whole numbers. So that brings me to the second question, which is when I look at something like oxygen, which has an 8 and a 16, can I find the mass number on the periodic table? The answer is no. Yeah. This number on the bottom here is not the mass number. It is the atomic number, not the atomic, it is the atomic mass. That's actually what it is. And the way you can remember it is the very last thing that's on that slide. All of those numbers need to be positive whole numbers. If you look, and you got great eyesight, or you got a periodic table near you, if you look underneath the symbol, pretty much none of those numbers are whole numbers. They're all decimal numbers and stuff like that. So that number, which is commonly mistaken for the mass number, is not the mass number. It is the atomic mass, which we'll talk about in a later chapter. Now, what usually confuses people is the idea that the mass number and the number that you see on the periodic table oftentimes are relatively close to each other. So maybe you got like a 52.999 or something on the periodic table, and your mass number is like a 53 or a 52 or something like that. So a lot of times those numbers are very, very close to each other, and they're really all based off of protons, electrons, neutrons, and their masses. But they definitely should be a mass number that is a whole number. That means in problems like this, you will be given enough information to calculate the number of neutrons or the mass number from the information within the problem as well. So the only thing that you can find on the periodic table is the atomic number. Mass number will not be there. As I mentioned before, again, remember hydrogen, the only guy that does not have neutrons. So isotopes are really good. They do basically behave like each other because they are the same elements. And this is a very common way that we write isotopes, like we see on the bottom. We use the chemical symbol. And on the top left of the symbol there is where we write the mass number. On the bottom left there is where we write the atomic number. And for example, this is hydrogen that has 1 proton and no neutrons. Deuterium is sometimes referred to as heavy hydrogen, has 1 proton and 1 neutron. Tritium is like the radioactive version of hydrogen. It has 1 proton and 2 neutrons. If we were to write the symbols for this, we would go 1 proton. You would simply go to the periodic table and find number 1. And if you weren't sure what hydrogen is you see H there. And we would put up there on the bottom left, or down there on the bottom left, would be 1, which would be our atomic number. In this case, in terms of our mass number, it is 1 plus 0, which is 1 for the mass number. And that would be the symbol there for hydrogen, 1 on top, 1 on the bottom. Typically, if it's written like this, you subtract the top number from the bottom number, gives you the number of neutrons. So 1 minus 1 is 0 for the number of neutrons. Now, if you go to deuterium and go, I don't know what that is, I've never seen it in my life, but you know it has 1 proton. Again, you simply just need to go to the periodic table and find number 1, which would still be the hydrogen symbol. And it would still have a 1 on the bottom there, which is its atomic number. And in this case here, though, it is 1 plus 1, which gives us 2 for its mass number, which would go up there on the top left. And once again, if you take 2 minus 1 there, top number minus the bottom number gives you 1 for the number of neutrons that is in this case. Once again, if you weren't sure or knew that tritium was, say, the radioactive version of hydrogen, you can figure it out very simply by, again, seeing that it has 1 proton. You could go to the periodic table, and that would obviously give you your symbol, which would be 1 on the bottom. And in this case, obviously here, 1 plus 2 gives us 3 for our mass number. So these would be the symbols here for hydrogen, deuterium, and tritium. They're all basically hydrogen because they all have 1 proton, which means they're all basically the exact same element, even though they have some different names that are going on there. Any questions on how to do that there? Another very common way that isotopes are sometimes written is kind of like I wrote a little earlier, say something like copper 64, for example. 64 is the mass number. And I know that because I could go to the periodic table and find copper, which is Cu, and I believe it should still say 29 above it. And I know that really 29 is the atomic number there for copper, which means if I wanted to write it a little different way, it would be 29 on the bottom, 64 up on top. And if I wanted my number of neutrons there, I would take 64 minus 29, gives us 35 neutrons. Any questions on how to write isotope symbols and stuff like that? Okay. So why don't we try some here for each of these, figure out how many protons, electrons, and neutrons there are. First off, CO, which is cobalt. This top number is our mass number. Bottom number here is our atomic number. And obviously the number of protons here would equal the atomic number, which is 27. In this particular case here, we know there's no charge because there's really nothing written here. So that is obviously typically where we would find a charge written. And since there's nothing there, we know it is neutral. So obviously in this case, since it has 27 positive protons, the number of electrons in this case would also have to equal 27. Again, 27 positives, 27 negatives gives us no charge overall. The number of neutrons can be found by taking our mass number minus our atomic number. So our number of neutrons in this case would be a 60 minus 27. And I think that is a 33, if I am not mistaken in this case. Any questions on any of those there? Looking here, same thing. Once again, we do not see anything written there, so we know that it is neutral. We can start with our protons, which once again should be the bottom number, which is our atomic number, and that would be 17 positive guys. As we established, no charge, which means we should have a matching number of negatively charged electrons in this case. And once again, our number of neutrons here would be our mass number, 37 minus 17. I'm going with 20 on that one there. Looks like a winner. Any questions on that one there? Lastly, U, which is uranium. Once again, I do not see any type of charge there. Starting with our atomic number, which is our bottom number there, gives us our 92 protons, giving us an equal number of electrons in this case, and our number of neutrons here, once again, our mass number minus our atomic number, a lot. That's like a 146 maybe, yep, give or take. How did I do on that? There we go. Not bad. Any questions on how to identify or calculate those guys? Obviously, you can see they are all whole numbers. Yes, no decimals. If you find yourself writing decimals for these guys or writing the number on the periodic table on the bottom there, you should just mark it off yourself. Save me my pen. Yes, because it would definitely be wrong. Any questions on anything we talked about here today? All right, I think it's a good place to lay it up for now.